Here we are going to see with certain concept known as priority level and sub-priority level. So in Cortex M3, we already know that there are fixed high priority interrupts. So that are shown in this negative numbers that you cannot change. And up to 256 levels of programmable priority. 256 levels of programmable priority, but maximum 128 level preemption. Why this 128 level we'll see later. So maximum 256 levels, but 128 levels of preemption. Right. But in most of the controller chips, I told that these many levels will not be there. Only the manufacturer will be supporting only 128 levels preemption will not be there. They will be supporting only 8, 16, 32, 64, etc. In the priority level is done by removing certain bits in the priority level configuration register. So let us take this is the priority level configuration register. This is a priority level configuration register. So here whatever it is shown in this gray color is not implemented. It is not there. Right. So only 3 bits are there. So since only 3 bits are there, how many priority levels you can have? Only 3
7.
bits are there. How many priority level? It will be like this: 0, 0, 2, 0, 4, 0, 6, 0, 8, 0, A 0, C 0, E 0. All these will be always taken as 0. Then the remaining you can find out 0, 0, 0, 0, 0, 1. So when it is 0, 0, 1, it will be 2, 0. 0, 1, 0, it will be 4, 0. Like that. So see, when you are having 3 bits implemented, you will be having only 7, 8 priority levels. Right. So you will show, they are showing one example. So here these are the priority levels in the case of 3 bits implemented. 8 levels will be there. And this is in the case of 4 bits implemented. So when you are having 4 bits implemented, in between each of these states, one more state will be coming. Right. So it will be 0, 1, 0, 2, 0, 3, 0, etc. up to F0. Right. So these are known as the programmable priority. These are this. Right. So this is how they are reducing the number of preemptions. Right. So if all these bits are implemented, if 7 bits are implemented, you will be having 128 bits of preemption. So if you are, why they are reducing the number of bits? If they are increasing the bits, gate count and power consumption will be increased. Right. So that is why, in order to have a balance between the power consumption and the performance, they are reducing the number of bits. And minimum number of bits will be 3 bits, that is 8 levels preemption. Then why they are removing the LSB instead of MSB? Because they are keeping the LSB bits unimplemented. Why they are not removing these bits, MSB bits? Why? Because in order to make it the portable software portable software between all M3 devices. Here in this case, you are having 3 bits implemented, right? And priority level 5, for example, this is configured for IRQ0. Priority level 3 is used for IRQ1. So which will be having priority?
IRQ1.
So how you find out that? It is shown here. IRQ1 should have 3. IRQ0 should have 5. So IRQ, whichever number is lesser, that will be having high priority. Right. So now it is only 3 bit implemented. So in the case of 5 bits are not implemented, how we will write? If MSB is not implemented, what will be written? 0, 0, 0, 1, 0, 1. This is known as 5. This is known as 5. If the same application you are porting into another controller with 2 bits implemented. Let us take 2 bits implemented. Here for time being, I am making M must be not implemented. Right. So if I am porting the same, here it is 3 bit implemented. When I am porting this to 2 bits implemented processor, what will happen? The next bit also will be not implemented. Right. So total 6 MSB bits will be not implemented. And what will be the remaining number? 0, only 2 bits will be there. So IRQ 0. So from, let us take IRQ 0 is this, that is 101, that is 5. When you are removing 0 from that, what you will get? IRQ 0 will become level 101. IRQ 0 will become 01, right? IRQ 1. So what, when it is becoming 01, what will happen?
It has higher priority, so it will be executed.
So when you are removing 1 bit from this, you will get it as 01. When you are removing 1 bit from here, it will be 3 itself. Right. So IRQ 0 will be having 1, IRQ 1 will be having 3. So what is happening? Priority is getting inverted. IRQ 0 will be made as high priority when compared to this. Right. IRQ 0 will be having high priority when compared to IRQ1. So this problem arises because you are trying to remove the MSB bits when you are porting application between different Cortex M3 devices. So in order to overcome this disadvantage, they are not removing the MSB, they are removing the LSB. Right, so this is a reason for that. Then there is something known as priority group bits. Priority group bits. So in the priority level configuration, for each exception, the priority levels are divided into 2 halves. One is known as preempt priority, that is upper half, and lower half is known as sub priority. Right, we'll see one example here. Let us take this example. For this example, the width of the register is 3 bit. That 3 bit is implemented, and here 2 bits are used for representing preempt priority. 1 bit is used for representing sub priority. 2 bits are used for preempt priority. 1 bit is used for sub priority. Right. Why you are getting like this? Because this is coming under, because here I have set the priority group as 5. So what do you mean by priority group? This is a priority group settings. If you are setting to priority group 0, what does it mean? Bit number 1 to 7 will be preempt priority field. Bit number 0 will be sub priority field. So here, how many levels of preemption you can have? 128 levels. That is why the maximum is 128 levels. Because at least 1 bit should be sub priority. So remaining only 7 bits will be there. So 128 levels. But if I am configuring the priority group as 1, what will happen? Preempt priority field will be from second bit to 7th bit, and bit number 0 and 1 will be for sub priority. But here for our example, we have taken priority group 5. I have made the group setting as priority group 5. What will happen? 6 and 7 will be set as preempt priority. 0 to 5 will be sub priority. That is what is you can see here. 6 and 7 will be preempt priority. 0 to 5 will be sub priority. But here I am having only 3 bits implemented. So what will happen? I will be having only 1 sub priority bit, 2 preempt priority bit for group 5. Right. And what is the use of sub priority? What is the use of sub priority? Sometimes if two interrupts with the same preempt priorities coming, right? Then the decision will be based on the sub priority. It is written here, right? So if two interrupts with the same preempt priority is coming, the decision will be based on the sub priority bit. So let us take this is a preempt priority and sub priority, how it is being done, right? So here you are having 3-bit priority with priority group is set to 5. That is the same example. Priority group set to 5, 3 bits implemented. So how many preempt priority field will be there? 2. How many sub priority field will be there? 1. So what will be the the preemption levels? This is that preempt level with the priority group set to 5. Right. So how it will be? These two are the preempt priority. This will be the sub priority. So I will be writing 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. So these are the binary values. So if it is 0, 0, 0, what does it mean? It will be 0. 0, 0, 1 means it will be 1. Right. So what will be the sub priority and what will be the preempt priority? These two are the preempt priority. This is a sub priority. So if it is 0, 0, 0 means what is that value? 0. If it is 0, 0, 1 means what is the value? 2, 0. Then 4, 0, 5, 0, etc. So these two values 0 and 0, 2, 0 belongs to this group. Right. So here let us take one interrupt is coming with the preempt priority 0 and another interrupt is also coming with the preempt priority 0. So what will happen? The decision will be taken based on the sub priority. So this interrupt will be given high priority. When the interrupt is, because I am not generating the interrupt, no, it will be generated from some device. So those two devices with these two, I have configured it as this is high priority, this is low priority. But sometimes these two interrupts are coming automatically. This will be taken because the decision is actually done based on sub priority. All these things, all this value. That is what I told. Here, this is implemented internally. I will be configuring only the interrupt numbers, priority number. I am not bothered about all these things. But you need to keep in mind, you need to check how many bits are implemented. Only that you need to keep in mind. Right. The internal things, sub priority, preempt level, all those things will be handled by the processor itself. We are trying to understand the operation done behind that. Right. So, but before writing the program, you need to identify how many bits are implemented. If you know that, then only you can find out how many levels are there. If you are having 3 bits implemented, you will be having only 2 raised to 3 levels. So you cannot write a 9th interrupt. So that only you need to keep in mind. And I can configure this by these registers, priority level, priority group register, etc. So here, let us take this example. Here, how many bits are implemented? 3 bits. Which is the priority group I have configured? 1. So how many preempt priority field will be there? 2 to 7. Bit number 2 to 7. How many sub priority field will be there? 0 and 1. So in this case, whether sub priority will be there? Right. So if you are having only 3 bit implemented and if you are configuring it as 1, sub priority will not be there. So you should not do like this. Right. That is what is shown in this slide. If you are having only 3 bits, you should not configure the priority group as 1. Then sub priority will not be there. Then why I told 8 levels will be there maximum? If
2
you are
raised to
having if you are having all 8 bits implemented and the priority group is set to 0, right? Priority level register with the priority group 0. then you can see only zeroth bit will be sub priority, all other bits will be preempt priority. So you can have maximum 128 bits preemption. But this will arise only if all 8 bits are implemented. But generally, most of the controllers won't have that much bits implemented. Timing diagram representing interrupt, input and pending behavior. Right? Yesterday I told there is something known as interrupt pending. What does it mean?
I mean, two interrupts come at a time. One will be assigned pending and one will be executed.
So here, let us take you are having an interrupt request, right? So whenever an interrupt request is there, interrupt pending status bit will be set in the next cycle, right? Pending status bit will be set, and when the pending status bit is set, before that the processor will be executing. When the processor identifies this pending status bit, it will move from thread mode to handler mode and execute the ISR. It is a normal case. But let us take a situation where interrupt pending is cleared before processor is executing the start execution of the ISR. Here, since the pending status bit was there, that is why the processor has started the execution of handler. When it has started the handler, pending status bit will be made as low because this interrupt has been started. So it will be low until this interrupt is over. But in this case, interrupt request has came here, interrupt pending behavior as pending status bit as 1. After some time, it is made as 0. Right. But the processor has not started its ISR execution. Right. So when you are trying to clear the pending status bit before the processor execution starts, what will happen? It cannot find out that an interrupt has been generated. That means the ISR will not be executed. ISR will not be executed if we are clearing the pending status bit before starting of the ISR. Whatever interrupt is coming, pending status bit will be high.
Okay, even if it is not a nesting case, I mean, if you have only one interrupt, it will be.
Because that status bit shows that some interrupt is in the pending state. That means next that interrupt should be executed.
Okay.
It tells the processor that something is there, you should start execution now. Right? So when the processor starts the execution of the interrupt, pending bit will be cleared automatically. That is what is shown here. When the processor is starting the execution, pending bit will be cleared. Then the active status is cleared on exception exit. So there is one more status bit known as active status bit. Previously we have seen only one signal. So what will happen when the interrupt is generated? Pending status signal will be set. So the processor will start the handler. Whenever the processor is starting the handler, pending status bit will be automatically cleared. And what will happen? Interrupt active status bit will be set. So that bit shows that some interrupt is getting executed in the processor, and it will be keep on in the same state until ISR is over. When interrupt exit is happening or ISR is over, active status bit will be taken to 0. Right. So on exception entry, what is happening? Pending status bit will be cleared. Interrupt active status bit will be set. On exception exit, what will happen? Active status bit will be cleared.
Sir, here in the interrupt request clear by software refers to our ISR code where we will be clearing that bit, right, sir?
No, you are. That is what I told. We are not clearing. it will be cleared automatically by the processor, right? This is exception. So here this chapter describes about the exception handling mechanism in the processor. Be involved in this all this process. It is an internal working, but when you are trying to understand this, you need to have some idea regarding these things. That is why it is taken. Right? All the active status bit, pending status bit, all those things will be taken care by the processor and the NVIC alone. Generally, it will be taken care. Most of the things are taken care by NVIC. So this is a normal case. So this from here we will see some of the special cases. So if an interrupt source, that is same interrupt, continues to hold the interrupt signal for a longer amount of time. Let us take this as interrupt signal. In the previous case, it was only held high for little amount of time. After some time, interrupt request will be automatically made low. But this is a special case where interrupt request stay high or pulled up in the high state for longer amount of time. So what will happen? So initially, as you told, interrupt pending status bit will be set. Then ISR will start. Whenever ISR is starting, interrupt active status bit will be high. So ISR will keep on executing until this point of time. So after this, again, since the interrupt request is high, it will be taken as a new interrupt. Since it is again high, it will be taken as a second interrupt or new interrupt. So pending status bit will be again high. ISR will start new, again the same ISR will start executing, and active status bit will be high. So whenever the same interrupt source continues to hold the request signal high for longer amount of time, it will be taken as a new interrupt. Right? That means the same interrupt will be pended again. Then in the second case, if the interrupt is pulsed several times before ISR has started its execution. Interrupt is pulsed several times before ISR has started its execution. Then what will happen? Right. So when the interrupt request is coming, when the first interrupt request is coming, interrupt pending status bit will be high. After some time, ISR will start executing. So before starting the ISR, it has been pulsed several times. So what will happen? But it will be taken only as a single interrupt itself. Even though it has pulsed several times before starting up the ISR, it will be considered as a single interrupt itself. Right? Because it is pulsed before starting the ISR, so it will be pended only once. Then this is a third condition. Here what is happening? When the interrupt is deasserted and then pulsed again during the ISR. Say for example, interrupt request has made high, pending status bit was high, ISR has started, active status bit also is high, right? But before completing the ISR, the same interrupt is pulsed again. ISR is not over. Again it is pulsed before ISR is completed. So what will happen? It will be taken as a new interrupt. Right. So pending status, it will be pended. Pending status bit will be high again. So that whenever interrupt is exiting, new interrupt will be the same ISR will be starting again. Right. So when it is pulsed before ending of the ISR, it will be pended again, or it will be taken as a new interrupt. So these are the three special conditions of interrupt inputs and pending behavior.